Today, it is time for 3D Printer Fixed Up Part 4. Wait, Part 4? Yeah, Part 4. What's up everyone, Chris here, and we have been working through a series of videos where we're trying to bring some life back into my original 3D printer kit, the Geeetech Pro B. And we've been doing a pretty good job. We've gotten the print quality up a bit, we fixed a few issues, and addressed some safety concerns. But now we're going to continue on. And most of this video is going to be focused on the bed, because there's a lot of issues there that I want to fix and some upgrades that I want to make. But we'll also fix up our firmware so we have a good copy. We did start that in the last video, but we're going to finish up. And we are going to talk about stepper drivers. We could definitely use an upgrade. So let's get right into it, and we'll take a look at the heated bed. So we definitely have some work to do. This bed is long overdue for an overhaul. So I'm just going to start by taking the whole thing apart. We'll take the glass off. I want to look at getting some new style clips for that. And then I'm just going to spin off all the thumb screws. I made these a long time ago, and they've worked really well, but I want to go a different route. So I'm just going to take the heated bed off. And on these PCBs, this is a great time to make sure you're not wearing any holes. You don't want to contact any of those traces. That could be a problem or start a fire. This one's actually remained in pretty good shape, but we definitely want to redo the thermistor and make sure all the heater wires and everything are good. We'll do that here in a little bit. And then you can see on this printer, it's just a piece of acrylic for the bed frame. Not the best choice in the world, but we're going to work with it since that's what we got. Definitely need to clean it off a bit. But this is held on to some LMU 88 bearings with just some zip ties. And I think I'm going to go ahead and remove these just to check it out underneath there and see if there's a better way of doing it. So with the zip ties off, it does have a belt tied down here in the middle. I'm just going to back those screws out. And we'll lift this off, see what's going on. So we can kind of check the bearings and the rods and check the belt, make sure there's no wear or anything like that. This one actually does still move pretty smooth. You could go the extra mile and repack these, pull them out, but maybe we'll do that down the line. I don't know exactly what changes we're going to make, but I think we're okay for right now. And on the bed, instead of cutting holes in the acrylic for the bearings to set in, they've actually just added these pieces of acrylic. They've bolted these on, so this is where the bearing sets. You could actually gain just a bit of Z if you cut holes in this, if there was clearance. I would probably only go with 3 as well, just to make sure you weren't over-constrained. But that's probably why they use the zip ties, is because there's a little lenience in that zip tie to give you a bit of slop to allow for any tolerance issues. What I would like to do is use something like this. This is actually from the Bear build, but I think I can modify this a bit. So this is a spare LMU 88 bearing. These just snap in here. They actually have rings so they fit in the grooves of the bearing so they don't go anywhere. But this would replace the zip tie. We would still need our piece of acrylic to set the bearing in. It'd still go on here, but we wouldn't have to use those 2 outer screws anymore. We could just run screws from the top into this printed part, and then that part will have some nylock nuts in it. That should keep it a lot more stable than the zip ties. Now, will that introduce issues because it'll be a lot more rigid? We're going to find out. But I'm going to need to rework this part of it to be able to use the acrylic pieces with this kit, because they don't go down inside there as far as they do on something like a Prusa bed. You can see when it's set down in there, there's a bit of a gap, but we can fix that. And here's what I came up with. I just altered the Bear part. I did have to shave it down here on the top because it was catching on the acrylic gantry underneath. And I did make them a bit longer so they would contact the acrylic that holds the bearing in place. They actually clip the acrylic right here just a bit. I've got 2 M3 nylock nuts in there, and then I'm just going to snap them on all 4 of the bearings. There's grooves that fit in the bearing grooves, and then we can flip them over. On top of that will be your acrylic bearing holder, and then the acrylic bed will go down over the top of that. So we used to have 1 zip tie holding the bearing on, and then 2 screws that held the piece of acrylic in place. Now we're just using 2 screws to go all the way through, down to the nylock nut. That'll hold the bearing and the bed. I'm going to use M3 by 30mm screws. And as far as the part that actually holds the belt, this isn't the best setup. You've got a hole in the belt with a screw in it, and it goes into this metal block, but at least it's metal. I'm going to leave it for now. I don't think it's hurting anything, but if we see any issues, we can revisit this later. The bearings under here, the idler, and in the back of the motor, there doesn't seem to be any noise or play in them, so we should be okay with that. So all 4 of the bearing holders are on. We'll go ahead and set our acrylic down, and then try to line that bed up with the longer screw. I'm using the 2 center holes where the zip strips were. We got 1 started. We'll just work around and do all 4. And there we go. All 4 of our bearing holders are on, and I did go ahead and remount that belt holder. Now you might want to consider putting some washers underneath these screw heads if you have some extra, but we should be okay for the most part. There isn't a whole lot of flex on this, so we shouldn't have to worry about those heads breaking the acrylic too much. And it does run relatively smoothly. Again, I don't know about that 4th bearing. It'd probably actually be a better idea to move one of these to the center just so you had a 3 set up. That way there'd be a little bit of play if everything wasn't exactly straight. And with this acrylic frame, not everything is going to be straight all the time. But we're good for now. Let's move on to strain relief for our bed wires. So I found this part over on Thingiverse. The original part was by Peter Vroom, but I reworked it. So I put a through hole on it, and then I put a hole here in the back where I could put a nylock nut. That should make it pinch on that acrylic a little bit better, and then I'm going to drill a hole in the acrylic bed. So I drilled a hole right in the middle. The middle of this is somewhere around 111 millimeter. I think it's 220 total. And then this will just slip on right here, and we can put an M3 screw. That'll go into the nylock nut and hold it in place. We just don't want it moving around. I'm going to use an M3 by 18 millimeter screw just so it doesn't poke out. There's not very much clearance here in the back. And now it's on. That shouldn't go anywhere. It has a spot for a zip tie up here, but that should do for our wire management. Now let's move to the heated bed because we need a bit of fix up there. So when I pulled this apart, my thermistor just came out from underneath this Captain tape. The tape wasn't really well done ever. And this one was just sitting here, taped on, and the wires were pulled apart. I don't recommend you do that to a thermistor. You really want to use some sleeving. Now you can get this fiber sleeve. I think the last time I bought it was from Philistruder, but it's around. I would much rather see you use this on your thermistor. So I can go ahead and use this thermistor, but I'm going to remove the solder joints and redo it. So I'm going to put some sleeve on like that to protect the wires and keep them from getting shorted. Then on the wire side, I'm going to use some heat shrink. Then I'll solder the thermistor back on. Remember, these aren't polarized. It doesn't matter which leg goes on which. Do be careful. These are very fine wires. Then once you have your sleeve on, you can push it all the way up and your wires are soldered together. Then you can slide up your heat shrink. And then we'll use a heat gun to stick these down. But this will make sure there's no wires exposed. And that's going to be pretty important because of what I like to do next. I like to use a piece of aluminum tape to hold the thermistor down. And if you don't have sleeves and everything protected, you might run the risk of shorting something out. But I'm going to make sure the thermistor bulb is right here in the center. I usually don't put it inside the hole because I think it's more likely to snap it off, but somewhere close that you can kind of get an idea of what the top temperature is. And then I'm going to spread the wires a bit and put my aluminum tape on. Then you can force that down around the wires and the thermistor just to make sure everything stays in place. And just for an extra precaution, on top of that tape, I like to put a piece of Captain tape. And with the Captain tape, I just like to cover that foil tape and further stick down the wires to the bed just a little bit. Now we should be in much better shape and the whole thing's going to be a lot safer. Next up, we're going to talk about putting the bed back on. Now, most of these beds have adjustable screws and springs so you can level it. We currently have a BL Touch on there, and I'm hoping to make the printer pretty consistent so we don't have to do a lot of leveling. The sensor can do it for us. So I'm going to replace the springs, screws, all that with some standoffs. Now these are 3mm standoffs. I believe they are around 15 millimeters long. But I'm going to use a screw from underneath to attach it to the acrylic, and then some screws going down to put the PCB on. And anything that's around the PCB, I like to use nylon washers. So on both sides of the PCB, I'm going to use a nylon washer followed by a metal washer to hold it on. The metal washer will sandwich these down, but this will protect the PCB from anything putting a hole in it. Even though the traces on these beds aren't close to the corner holes, you don't want to risk that. So I'm going to do an M3 by 8mm screw, a metal 3mm washer, then a nylon 3mm washer. That'll go from the top through the bottom of the heated bed, like so. Then we'll do another nylon washer, and another metal washer. And then we'll screw on our standoff. And I'll just do that for all four corners. Then we'll move to fitting it on the acrylic piece on the printer. Now with the standoffs on the bed part, I'm going to do pretty much the same thing to attach it to the acrylic, only the acrylic's a lot thicker, so I'm going to use a little longer screw. I went with an M3 by 14, and I am going to use just some standard metal washers, one on the bottom of the acrylic and one on top before it goes into the standoff. So one closest to the head of the screw will go through the acrylic, one on the other side, and then it can go into the standoff. And we'll do all four. And the standoffs are on. Now you can use pretty much any standoff you have laying around. These are just the ones I had. Again, these are about 15mm high. You can use a little shorter one. You don't want to use them too tall because that will run you out of Z room. The shorter they're going to be, the more consistent your bed will be. But I think this is a good move going forward. We're going to use the sensor and let it do the leveling, and then we won't have any movement caused by those springs. And then our wire management piece here in the back, just make sure you zip tie the part down that has some covering on it. I'm going to set mine right in there. And after you get your strain relief on, make sure that you have enough clearance to move the whole Wham movement. We do. Remember, I did put a piece of that nylon in there to keep the cable just a little bit more rigid. But this should make things a whole lot better. So the bed's in pretty good shape. I do want to address how the glass sits on top of that heated bed. I found some clips that might be helpful, so we'll take a look at that. But let's finally nail down this LCD screen that's been floating around during this whole project. And here's our LCD controller and screen. It is just the standard rip-wrap style. It's the 2004. And I did 3D print some parts to help get this back into shape. First off, you'll notice it doesn't have any screws here anymore, so the PCB is actually just being held on by the knob. So I created some spacers to put this back together. They'll just fit underneath the LCD screen right here, and I'll put some screws on it. I'm going to use some M3 by 20s, and since I have some, I'm going to go ahead and use those nylon washers again, and just put a regular M3 nut on it. So that'll at least get our screen back in better shape. Now we have to attach it to the printer. Now on the original setup, this screen set up here on top. I moved it off the top to the front of the enclosure that I had this set in. Now I don't think I want to do that. I think I will have enough room if I ever want to put this back in the enclosure. I want to put the screen on the front, like a Prusa style. And I found these parts on Thingiverse and I worked them up to fit my needs. But this should let us put the screen on. I added these square nuts, but we can just use some M3 screws from the back and have it hold down to the acrylic. So these will just fit in the stock holes on the acrylic front plate, like that, and then I'll just use some M3 by 10s to grab that square nut I have there in the back. So there we go, one on each side, and then this will just hook on the acrylic. And those clips actually did fit pretty well without having to put the screw on the back. They're down over the acrylic nice and solid. They do shorten up my wide just a little bit, 5mm or so, because those bearings do hit. But without the screws, it is pretty easy to remove. I don't know how big of items I want to print on this printer, but I could just slide it off and lay it to the side if I wanted to. So I might rework these clips a bit, move them to the center so they don't clip that bearing holder, but for now, I think we're in good shape. Now let's talk about stepper drivers. On a printer like this that was made a couple of years ago, it's pretty common to see what we call an A4988. That was the most typical driver you would see, But now we have newer drivers that we like to refer to as smart drivers. Now the drivers on this board are replaceable. They are attached to what we call a step stick, or you might hear silent step stick. Basically, it's just a small PCB that houses the driver, so you can replace it if something bad happens. So we should be able to swap out the drivers on this printer fairly easily, but there's a lot of information that goes with stepper drivers. What type you want, what they do, how you configure them, what mode you want to run in. So I'm just going to go over the basics on the drivers. I do have other videos around these subjects. I will leave some links in the description. But this is kind of an old school board, so we're going to run in what is called standalone mode. Let me further explain. Now let's have a look at the printer's noise level before we make any changes. This was just the fans running. And here's just a quick test print to show you the noise difference. Again, the fan is a lot of it, but you can kind of hear the motor noise as well. So let's take a look at the drivers, what we have now. So these are the super common A4988s. You see these on a lot of printers, and these have some age to them, although they do still work. Now this is a bit of an older school board. Basically it's ramps integrated with a few different features. But you can replace the drivers, so these just pull out of the socket. Here's a closer look at one. And pretty much the only thing you can configure on these is current with the potentiometer that's on the front. And using these three jumpers, you can set your microstepping. The highest microstep on an A4988 is 16 times. You can also run the 8825, which is 32 times. So all three jumpers on, most of the time, that defaults to the highest microstepping you can do. Now here's just a handful of drivers I had setting around. Today we are going to go with a TMC 2209 that's made by Trinamic. It's kind of the go-to hobby driver for using a smaller motor like a NEMA 17. It has the most features and they're about the same price as some of the other drivers. Now running in standalone mode, we're not going to use all those features, but if we ever want to, we will have them, and again, it's not much more money. So this driver right here, this is a water rot driver. These are more high-end drivers just because of the board and how they're made and some of the components that they use. But they are quite a bit higher priced. This is our A4988 that we took off of the printer, just the standard old school driver. They still work just fine, kind of loud, no smart features. Then we have the Geeetech 2209 1.2 version. Definitely get 1.2s rather than 1.0s. The 1.0 had a few bugs. Also a 2209 chip. And then we have this Erie 1 stepper driver. It is also a 2209. Now, why are all these different? Well, let's just talk about the smart drivers. That water rot driver is actually a 2208, but for this example, it'll work just fine. All of these PCBs have the same type of chips, either 2208, 2209 from Trinamic. The driver's chips are the same, but how the board is configured is very different. You can run in standalone mode or UART SPI mode, depending on the chip. If you run in a UART mode, that enables communication with these drivers, so you can change things in the software on the fly, like reference voltage to lower or raise the current. You can use sensorless homing if you have a 2209, and you can adjust whether you're in stealth chop mode or spread cycle via the software, depending on demand. So there's a lot of things that will happen automatically if you're running in the connected mode. We are going to run in standalone mode, and there's some defaults there, and some of those are configured physically by pins or by solder points. So there's a lot of things here we need to worry about because these boards are configured differently. Now in the 2209s, they've kind of gotten it straightened out with most manufacturers, that you don't have to do much to switch in between UART mode and standalone mode. Most of the time you don't have to solder anything. That wasn't the same on a 2130. Because 2130 uses SPI and that's a little more complicated. So we don't have to worry about that so much. But when we're using the older school board, it would really help to have a schematic. And there are schematics for this GT2560 board. This is it right here. And that's all fine and good, but they don't give us any pin numbers and it's out of order. So that doesn't help a lot. The good thing is it's almost exactly like ramps. And this is the pinout for ramps board. And there's a ton of information on that board, so we are in luck. Now with that said, there are 3 jumpers on our board. I will show you. And this is really common on these boards or ramp style boards. This is how you configure what your micro stepping is for the A4988 or other drivers. It even gives you a little graph down here which ones to leave on or off to get the right micro stepping. So all of them on are 16 times. Like I said before. Now back to our schematic. That's what these are representing. And if you have the schematic, you can tell what happens when you put those jumpers on. We have our jumpers MS1, 2, and 3. If you put the cap on, that sends them to voltage and makes them go high. Now that's logical voltage anywhere from 3.3 volts to around 5 volts. But also take a look right here. These 2 pins, reset and sleep, they're connected together. And I'm not exactly sure what those controlled on the old school stepper drivers, but I know that you had to have them connected before it would be activated. And that's not how things are done on a lot of these newer step stick boards. But be aware, these 5 pins right here are the ones we're interested in. So this is how the board is configured. Now let's take a look at some of the drivers. Here is the Water Rot silent step stick that has a 2209 on it. Now this is the bottom of the board, so imagine that this is flipped over. We were looking at the top of the schematic on the board, but this is the bottom of that step stick. So your enable pin would be up on top, and so on. But again, we're concerned about these pins. There's 5 of them. So MS1, MS2, those are fine. Those line up with our board. But the next pin down actually sets spread cycle. So if you set that pin high, you'll be going into spread cycle versus the stealth shot mode. And then you have PDN and UART pins, these 2 right here. Now PDN allows you to communicate with just one wire. And you'll notice these jumper solder pads right here. On most of these drivers, this allows you to select one pin or the other. So you can use both of them for dual UART mode or just one for PDN. You would hook both wires up, but one wire here and the other wire would go in with a 1K resistor. Since we're not using UART mode, we're not going to go into that. There are schematics available on how to set that up. The main thing I want to show you is the differences in between these different PCBs. So this is Water Rot. Let's take a look at the Big Tree Tech. Now they did flip this one the same as my schematic for ramps, so it's a little easier to understand. But again, these same pins. MS1, good. MS2 is good. You have your PDN pins, it's the same as UART. But down here you have what is called a clock pin. So it's configured differently. Also note that the diag and VREF pins up here are in different locations on the board. And when you buy a Big Tree Tech driver, they're going to have that diag pin facing down because they intend for you to use these on an SKR board. And sometimes depending on the board that you're going to use them on, that diag pin down will conflict with other components. Like this board we're dealing with here, we have a capacitor that it might hit. So be aware of that as well. And then we have a picture of our Erie 1 board. Now the reason why I selected these to go with this build is because there was almost no information on them. So I wanted to be able to try to figure out how to use them to share it with you. Notice here we do have the MS1, the MS2, and our UART pin. Next to it they've labeled it PDN, but both of these are configured. You can use either one of them. And if you notice on the bottom right here they have this little resistor. All this does is select whether you want to use the UART pin here or the PDN pin. So if you were to move that resistor over to these 2 solder pads, that's going to get you over to this PDN pin. And there's a reason why you might want to do that, but we'll talk about that in a second. And then you have your spread cycle pin. So if you set that one high, you'll go to spread cycle. So let me try to pull this together. Let's go back to our ramp schematic. This is the driver we are going to use. So remember we have our MS1, MS2, MS3, reset, and sleep. Reset and sleep are connected together on this board. Back to our driver. We are going to use MS1 and MS2. Those will select our micro-stepping. So we're going to put both on. That'll get us into 16 times with interpolation on. I'm making some assumptions because that's how a lot of these drivers work. Again, no documentation on this one. But then we have the UART and PDN pins to deal with. UART is fine where it is in this configuration because this resistor is on, so you are using this pin. Just as long as you don't put the MS3 cap on. You don't want to set it high. You won't be using the pin that goes down, you would only be using the pin that goes up. Then PDN, this pin isn't active because this resistor is on these two solder pads. You would have to move it over to here. And then spread cycle is setting in the sleep pin spot. And that's all fine and good because sleep and reset are just connected together. There's no voltage. So you could jump 5 volts or 3.3 volts over to this driver with another wire, put it right here and turn spread cycle on if you wanted to without impacting the board. But that's only if you're not using this PDN pin. If you are using this PDN pin and you jump over to spread cycle, remember these two are connected underneath together. So you would be feeding voltage into this pin. So in that scenario, you would have to cut the bottom pins off and not feed them in the board. The biggest lesson is using this driver on this board, we don't have to make any pin changes and we can just control them with the jumpers without hurting anything. But there are so many different configurations when it comes to these types of boards. You need to know all about them before you try to use them. And that was a whole lot of information and it might be really confusing. But basically, when you go shopping for a driver to use on your board, don't buy anything that doesn't have a full set of schematics or a manual telling you how to use them, because they do vary greatly. Make sure they support the mode you want to use, whether it be standalone or UART SPI mode, right out of the box, so you don't have to mess with solder pads. You can control everything with either software or a jumper cap, or by adding a wire to a different location on the board. Make sure all that information is available. Now back to the board. So this board right here, we have MS1, MS2, and MS3 jumpers. Remember we saw in the schematic, we want to pull MS3 because on these stepper boards, that is the UART pin we're currently using. And we'd feed voltage into it if we left this cap. So we're going to pull all the MS3 caps. Now we can go ahead and plug in our drivers. Now driver boards like this, the one we're going to use from Erie 1, most of the time they're going to be flipped upside down from what an A4988 would be. So your A4988, you have direction and ground pins here. The potentiometer would go down on the board. You can consult that same schematic we saw for ramps. And then on this board, on your Erie 1 with the trinamic on it, your potentiometer is up here at the top, and you have ground and direction down here. So the board is configured the same, but the potentiometer will go up to the top versus this one down on the bottom. Just make sure you match the pins up, because if you get them backwards, you could ruin the driver. So now we can just install the drivers where the A4988s were. And I have all 5 installed, and I'm not going to use that 5th driver right now, but I went ahead and installed it just in case we want to use it on this project down the road. Now we should be safe to go ahead and turn the printer on, and I want to set the current of these drivers. And in this mode, when you're not using the UART pins, you use the potentiometer on the driver board to set the current. There's a reference voltage there. And you don't want to use the center of the potentiometer on these like you would on an A4988. You actually have a reference pin, or at least a port for that pin. And those are different on these boards as well. On these drivers, the pin that you want to measure with is this one down here below. The one up top will actually give you reference voltage of the driver, so around 5 volts. The one for the actual current measurement is this one down below. So now we need to get a measurement with our multimeter. What I like to do is just take a jumper and get a good ground from the power supply in. So I'll just slide it past this wire down here, and I'll attach my negative lead from my multimeter to that. And we'll take our other lead and we'll measure the reference voltage. And I'm going to adjust all these, but I'm just going to do one so you can see it. But I'll touch that spot on this driver. We're setting at 974. I usually like to start around 800. So I'm going to set all of these around 800. You can probably go less. If your drivers start to get just a little bit warm or your motors get warm, we can turn it down. But if we turn it down too much, we might start skipping. So on that potentiometer, I'm just going to use this tiny little screwdriver and turn it down a bit until I see roughly 800. I'm good with 815, and then I'll move on to the rest of the drivers. You want to make sure you check this before we do any testing, just in case they're way too high. Now with our new drivers installed and our current adjusted, we're just going to do a quick test movement from the LCD screen so I can show you what's going to happen. I'm going to try to move X in the positive direction, and you'll notice it's moving in the negative direction. And that is really common when you go to this type of driver. They're going to turn the opposite way. And that's going to be for all of them because we switched from A4988s over to Trinamic. So we need to adjust that in the firmware. So our next step is to head over to VS Code, and we're just going to search for DIR for direction. And you come down to your inverted motor section. So we're just going to flip-flop all of these. So X is true, we're going to make it false. Y is true, false. Z was false, true. And E, make that one false as well. And I'll go ahead and change E1 because I do have a driver there. And it's also a good idea, since we were running A4988s before, is to update your configuration to tell it you have 2209s. The default config does use A4988s, even if you have this commented out. And running with that configuration in a 2209 standalone mode isn't going to hurt a lot, but it is good practice to make sure they say the right thing, because chopper timing or something specific to that driver could be different. So we're going to uncomment all the drivers we're using, Y, Z, E0, and E1, and we're going to change A4988s to TMC 2209 standalone. That will cause it to ignore all of the configuration options in configuration_adv.h, where you can configure it to talk UART mode, like centerless homing, or adjust the motor current. But any changes there are to the signal that it provides to the driver for 2209 should be there. So those are all the updates. We can go ahead and upload to the printer. Remember, we're still in the 2560, the Mega 2560 environment. Our upload was successful. Now we can go ahead and test our printer one more time. I'm just going to hit Auto Home because now I have faith that everything should work. And our Auto Home was successful. So pretty much all the fixes or upgrades I wanted to do in this video are done. I do want to address a couple more things. One being the bed clips. I get really tired of those binder clips you have to use to hold the glass on this type of PCB. So I want to look at a different style of those. And we also do have to dial in our Z offset because we never did that when we went to the new firmware. And then after we get that done, we can run a test print. So let's get back to it. So for bed clips, I'm going to go with these Swiss clips. These things are actually intended for picture frames, but some people say they have good luck holding down the glass with these. They would actually work a little bit better if the bed surface was a little thicker. We just have that thin PCB, so I'm going to wedge a piece of foam underneath the bed and clip to kind of hold it on a little tighter. We'll see how these go. I was able to get 5 all around the bed. They're just barely gripping that glass, so we'll see how they work. But anything is better than those binder clips with the arms hanging off. Those like to get tangled up on the hot end as well as the BL Touch, so we'll give these a shot. Now let's move back to the firmware for a second. Wait, hold the phone before we do anything firmware. When I was putting those clips on, I just realized something. This printer has been assembled incorrectly this whole time. If you've noticed in some of the other videos, these rods up here that support the X are a lot longer than the axes. And the Y-axis actually has just a little bit more threaded rod to it, so you could expand it. That's because these rods were supposed to go on the Y, these rods were supposed to go on the X. And because I've never altered the belt or anything on this, I know I never flipped them. So when I put this together originally, I did it wrong. So all this time, I could have had a little bit more build volume. Live and learn, I'm going to go ahead and switch that out. And that only took about an hour, but that's much better. These rods fit great, and I get a little bit more room. Now on to the firmware. So I was just scrolling through the firmware, and they've made some configuration changes in here that I'm not sure why they did them, but I want to change it up. Remember, this was the default config out of the Marlin folder. The first thing I come to that I need to change up is PID tune. I want to run an auto tune and put the new values in here, so we'll do that after I upload, and then I can update it. Also, PID bed tune, I'm going to turn that on, and we'll do an auto tune for the bed as well. Default max feed rates, I want to change these up. I think 400 is a little too high. I'm going to go down to 200 on X and Y. But then on Z, I'm going to jump up to 12, because the Z moves really slow on this printer. And extruder, I'm going to do 120. Max acceleration, 5,000 is definitely too high. I'm going to change these to 1,000, X and Y. Z will go 1,000 as well. And then the extruder is fine at 5,000. And then maximum for print moves, 1,000 is probably okay, but maybe 1,250 is better. Same for retraction, let's do 1,250. Travel Excel, 3,000 should be good. Junction deviation, they have it set at 4. I'm more comfortable at 3. This is instantaneous movements, basically. It replaces jerk. We can tune that after the fact, but I think 4 is a little high. Our probe offset we set in the last video. I do have it set for 0 on Z because we need to tune that in. Probing margin is 10. That's okay. That just keeps it from the outside of the bed. I'm still comfortable with 10, even though we have the new clips. X and Y probe speed, we'll have to see how this goes. 133 times 60. With the new values we just put in for feed rate and acceleration, it probably goes a lot faster, but it does home really slowly right now, but I think it was because of those values. So we'll check that. Multiple probe 2, that's fine. 200, 200 on bed size, we can go ahead and leave that, but I do have a negative position on X and a positive one on Y. And just to show you what I mean, the nozzle is actually outside the bed when we home, and it's about 2 millimeters or so into the glass when we home. That's what you want to set those values as. So I'm going to keep negative 12 on the X, and since we moved around the bed size with those Y rod changes, I'm going to take this one to positive 5. Bed leveling, we set this up before. It's just auto bed leveling by linear, and we're doing a 3x3 grid. That's okay for now. And our feed rate homing speed, 50 times 60 and 4 times 60. We'll just see how it goes. Again, I think those feed rate changes should help this. One other thing I did notice, they have disabled M503. On a 2560 chip, you should have plenty of room for that. So I'm going to comment this out so I can use the M503 command to get a little information about what the firmware is doing. And the LCD screen on this one is a little finicky. You have to turn it too many times to go to the next menu item. So I'm going to uncomment this line. We'll just set it to 1 and see if that fixes the problem. We can also do the encoded pulses up here. 4 pulses per step. We might have to mess around with that too, but we'll start with this one. And everything else, I think we should be in good shape. So let's go ahead and build and re-upload. So we got this error when we tried to compile, and that's pretty common when you're messing with these Y and minimum positions. So let's take one more look at it so I can explain it. It's saying when it does the math for Y min and Y max, they're too narrow to contain that bed size. I think the easiest way to understand it is to just do this with a ruler. They've entered some sort of math problem in here. I actually like to just put in the values. So my nozzle is actually about 5 in from where we are at 0 on the Y. So that's where we get our 5. And then if we go all the way to the back, remember we're losing some room because of our LCD down here. And we measure again, the nozzle is actually setting at 196. So that's the maximum travel position. And you want to try to get as much bed volume as you can, but most of the time you don't want to get all the way out to the edge. So X is working just fine, we'll leave it. But we're going to call our new bed size 190. And then our max Y position would be that 196. You could make this 191 if you wanted to. But that way, both of these numbers will fit inside that Y max position. You got 190 and 5. This just keeps you safe so you won't crash. And I'm not really worried about a couple of millimeters of build volume with this printer. So that'll allow it to build. Let's go ahead and build and upload again. And while that's building, let's go ahead and go into the slicer and talk about a few settings in here. We definitely want to use linear advance on this machine. And for a direct drive extruder, I like to start at a value of 0.08. Even after you do the calibration, this usually works pretty well, but it's going to help print quality a lot. So I've got my default PLA here. That's what I use if I'm not using a Prusa profile. And it doesn't hurt to run the M900 command if you don't have linear advanced enabled on a machine, and a lot of these machines don't. So I'm just going to add this to my default profile. This is the filament profile, M900, and your K value of 0.08. We can go back and calibrate that later, but this is going to work for pretty much all these direct drive machines. For PLA, of course, you will be a little different for PETG and different filaments. But this will get us started. We can go ahead and save this. We can add a LA on it so we know linear advance is there. We can even put 0.08. So that's the only thing I need to change in the slicer today. And our upload was successful. Let's head back to the printer. Let's open up Pronterface. I want to make sure that my new M503, now that it's enabled, is working. And it is. I'm going to do my auto tunes. So M303, you've seen me do this a bunch, but E0 for the hot end. C, 10 cycles, and our target with an S, we'll do 210. And we'll let that run. Okay, the hot end PID tune is done. We still need to do the bed, but while I was waiting, I noticed some things up here in our M503 output that need to be reset. And if you get this pause for user, that means it's waiting for you to click the knob on your LCD. But let's go ahead and reset EEPROM, M502 to pull in defaults, and we'll resave with M500. Let's take another look. So it updated our junction deviation, so now I know it pulled in my settings that I changed. But I noticed this as well, this skew factor. So in this example config, they've actually enabled skew compensation. So this config is actually really custom for an example config. You usually don't see that. But we definitely need to turn that off until we've calibrated it, even if we want to use it at all. But now we have our hot end PID numbers. Let's go ahead and run it for the bed, and then we can go back and update that config one more time. So for the bed, just do E-1. Set your cycles, however many you want to do. I'll just keep it at 10. And then S, I'm going to shoot for 60 as my temperature. And we'll let that run. So while we're waiting for the bed to run, we'll just comment out these PID values for the hot end and paste in our own. And let's go down and find that skew compensation. You can always tell because they give you this little graph right here. That's how I know where it is. I'm just going to turn it off. We'd have to calibrate it anyway to even be able to use it. So we don't want to use it on this build. Now we'll just wait for that bed PID to complete. And here are our bed numbers. We'll go ahead and grab these and update them. We'll just comment out the defaults again. Make sure you're in the bed section. You can see PID temp bed right here. And we'll paste in our values. Now we should be good to upload, and then we'll move to configuring the Z offset for that BL Touch. So our upload's complete after the PID changes. I'm much happier with this firmware now. I'm getting used to the config file. Let's go to Pronterface. Let's make sure we have everything pulled into EEPROM, M500, M502 first, then M500, M503. Everything looks good. I did make one more change to feed rates on Z. I set it to 12 originally. I moved it down to 8. I got to thinking about it. This acrylic frame probably can't handle 12, so we'll test it with 8 for now. Everything else should be good. The last thing we need to set is the Z offset. So let's ballpark it first, and then we can use baby stepping to dial it in. So we will set the bed to 60. Let's home the machine. Then we'll run our G29 leveling sequence. We'll just wait for this level to complete. The level's done. Now we'll move to the center of the bed. And I'm just going to put my piece of paper underneath the nozzle. You've seen this a bunch of times, I'm sure. I'm just going to lower down Z. We do need to turn off software end stops because we will need to go into the negative. So you can do that with M211, S0. And then we'll just bring it down slow. It's pretty common to have a large offset when you're using a BL Touch, just by the way it's mounted and used. There's -1 millimeter. There's -2.14. Let's start with 2.04. That's good. Let's just save it in EEPROM to get us started. You can also see where that is with an M114. But let's do M851, Z, -2.04. And we can save EEPROM, M500. And I'll also go to the firmware just to make a note so that next time we want to use the firmware, it'll be updated. That gets updated right here, -2.04. And after we do the baby stepping, I'll come back and adjust it one more time, just so I don't forget. And just to dial in the level with baby stepping, I like to use this leveling print that Tom made a long time ago. It works pretty good. So let's kick the print off. So we started the print, we went through the auto level. It's looking quite a bit too high all the way around. So let's double click to get into baby stepping. Mine is configured to set that offset. You can see the one we have here, 2.04. Let's bring it down a bit. I actually brought it down a lot. I ended up with 3.078. But it is sticking pretty well, and it seems to be pretty even around the bed. So I'm happy with that offset. I'll make the update in EEPROM and in the firmware for safekeeping. We'll go ahead and stop this one for now. And now let's give the Benchy a try. And we're off. Let's let this print, and then we'll take a look. And here's what we ended up with. We do have some stringing. There is a band around here at the bottom, maybe some over extrusion. I think the Hotend is actually printing a little hotter than it should be. I'll get the temp probe out and test that. We might have to make a thermistor change. But this one, compared to the one from the second edition of 3D Printer Fix Up, it's much improved. The biggest being the driver change. You don't have that candy striping that you see a lot of times on the wheelhouse in here. So we've got work to do, but I'm definitely happy with the upgrades that we made. And now I'm pretty comfortable about going into the slicer and starting to tweak settings from there for this printer. The firmware should be pretty solid, and the hardware is what it is, but we can probably still make a few improvements on that as well. So we're getting there. And we have reached the end of 3D Printer Fix Up Part 4. Now we did fix a few things in this video. We have just a little bit more stable firmware. It should be ready for others to use. And we did spend a bit of money. Those 2209s aren't all that cheap, but I do think they're worth the price. Given their silent nature, they do improve print quality, and if we want to go to UART mode later, we can use the added features that they will bring. Remember, not all silent step boards are created equal. Make sure you have all the documentation you need before you purchase them. Now, there are a few more things that I'd like to address on this printer. But for the most part, I'm pretty happy with how it came out. And it's way better than when we started, if you compare the first prints from the original video to today. And that always makes me happy to see. So that's it for today. I hope you liked this video, and I'll see you really soon on the next one.